I was thinking I didn't explain the bit about why with the quasi-chemical model with Z is 2, you can never get a miscibility gap, but you do with Z is 6. I think I didn't explain it too well. If you have a linear lattice, a one-dimensional lattice, then let's say as your cluster size, as the omega becomes more and more positive, the cluster size, which is a chain, you have a long bunch of A's and you have a long bunch of B's and you have another bunch of A's together. The chain size can rapidly become quite long, and as the chain size becomes long, the number of A-B bonds decreases quite rapidly. Okay, so the A-B bonds, remember, are not favored. They're the ones that are not favored. They have a positive energy. Okay, so you're trying to reduce the number of A-B bonds, but at the same time you're trying to increase the entropy. So quite rapidly the number of A-B bonds are decreased. The system has no real reason to split into macroscopic phases because, let's say your average chain length is 50. If your average chain length is like you have 50 A's and then 50 B's and then roughly, this is average, 50 A's. Then you have 50 AA bond, 50 BB bonds for every 2 AB bonds. So right away you've got 100 AA and BB bonds. You've already limited your number of AB bonds down to 2. You're getting rid of them really fast. But let's suppose you have a 3-dimensional lattice and you have a cluster size, which is a 3-dimensional cluster of 50. So now consider yourself a little cube, well, let's say 64, so you got 4 by 4 by 4 by 4. So you got a cube that's 4 by 4 by 4, so that's a cluster of, say, 64 A's. But on the surface you have a huge number of A's. Almost all the A's are on the surface. So the number of AB bonds to a neighboring cluster of B is still very large. Your cluster size has to get very large before you decrease the number of AB bonds significantly. Okay, in 3 dimensions, even 1,000, if you take 10 by 10 by 10 cubed, you got 1,000 atoms in there, but you got 400 of them around the surface. So they're forming a lot of AB bonds. So the system, by just forming clusters within a single phase, cannot decrease the number of AB bonds rapidly enough, so it actually splits into 2 phases, the way it does in 2 macroscopic phases, as it does in the Bragg-Williams model. The Bragg-Williams model, it can't reduce them, so it simply splits into 2 phases. Your Gibbs energy as a function of composition looks like this. It splits up into 2 phases. It just can't do it fast enough. Now I know this isn't quite totally mathematical, but this convinces how you can work. So it's or if you like it, this is your grain boundary, and your grain boundary just doesn't contain it. If you have a cluster of 100 A's, you've almost all A's. You hardly got any A's are on the grain boundaries. But in 3 dimensions, if you have 1,000 A's in a cluster, you've got an awful lot of grain boundary. Almost half of them are on the grain boundary. So you can't decrease the entropy fast enough, or the enthalpy fast enough, just by keeping a single phase with big clusters. It's better to split into 2 phases. You can decrease the entropy, but you can do it better. Enthalpy, you can do it better if you split it into 2 phases. Now to prove it mathematically, I can't, because I can't do the 2-dimensional Holzhauer equation, but I've been told that when you do it by molecular dynamics, making the appropriate assumptions, it does work out that way. It seems possibly only Ising didn't realize that, I don't know. I've never seen that written anywhere as the explanation for it, but I think that's it. Okay, one other little thing I talked about the other day. Here's your full equation now I talked about how why Z equals 2. Okay, you only get the entropy expression is only exact if Z equals 2. That's when ZA equals ZB. If ZA doesn't equal ZB, how do you make it exact? Or how not, well, then it's not exact. Because if ZA does not equal ZB, you can't have a one-dimensional lattice, so the whole thing is a bit silly. But what we're going to do then is we're going to take the entropy expression here, configurational entropy expression, and in the configurational entropy expression, what I want to do is I want to set omega, or I want to set delta G AB equals to minus infinity, so you have complete ordering. I want to then have delta S. Okay, and this is the point where ZB, this is the ZB over ZA, whatever point, and I want it to be equal to 0 at that point. Okay, so let's say ZB over ZA equals 2, then this point here occurs at XB equals 1/3, or YB equals 1/2. What values of ZB, what ratio ZB over ZA, or what values of ZB over ZA do I have to choose in order, if I want my minimum to be, when omega is minus infinity, I want my minimum to be at 1/3, but I also want it to be the excess entropy, the configurational entropy to be 0. What values of ZB and ZA do I have to choose? So if ZB over ZA equals 2, you'll actually find the right answers are ZA has to be 1.3774 something or other, and ZB has to be 2 times ZA. But to prove that, what you want to do is you want to go to this equation here, go to the, I'll let you play with this yourself, take equations 2 and 3, which are the mass balance equations, and this would simply say that NAA plus NBB plus NAB, which is the total number of bonds, from putting together the two equations here, is equal to ZA NA plus ZB NB over 2. Or if ZA equals NB, then it's just ZA times N total over 2. Then we're going to substitute that expression back into the expression down here, number 10. So I'm going to get del des configurational. Remember, this is the del des configurational for NA moles of A and NB moles of B. So let's put that into here and convert this back into per mole of solution. Then these NAAs becomes the XAAs, so we're going to have del des configuration was minus R NA log XA plus NB log XB. I'm not doing this per mole of anything now, I'm actually writing the total number of moles out here. Minus R ZA NA plus ZB NB over 2. And now this term then can become XAA log XAA over YA squared, etc. And so now what I want is, I want the delta S to be 0, I want ZB over ZA to be 2, and I want delta S to be 0 when delta JB is minus infinity. Okay, so when delta GAB is minus infinity, XAA will be 0, XBB will be 0, XAB will be equal to 1, and so on, and do the substitution, and you'll find out how it works for any ratio of ZB over ZA where you want to fix the minimum. You can find how the ratio has to work. This is purely mathematics, it's purely artificial. But that's why when we're doing the oxide database and that, where we tended to use Z equals 2 in quotation marks, but we can't use Z equals 2 because we want ZB over ZA not to be equal to 1. But we still want delta S to be 0 when delta G is minus infinity, so these are the values we turn. The average is roughly 2, but that's why we chose those values. And if you want the ratio to be 2 to 3 or 3 to 4 or whatever you want, these are the ratios that we... Now you don't have to have it exactly 0. There's absolutely no reason why this couldn't be 1.5 and that 3. That would still give the minimum here, but at minus infinity it would be a little bit below 0. So this is... But that explains why we did that. Well, the real shortcomings, if you want to sum it all up, of the quasi-chemical model is this approximate expression for entropy, which leads to all this other problem. Doesn't seem any way around that. All right, let's go to the last complication in the quasi-chemical model. This is the Z, the variable Z's. Any problems up to here? All right. So we have got a way. First of all, we started with Z as constant. We said, well, that's not so good because in the binary systems you have minimum that are not at 50%. So let's introduce ZA and ZB to be different. Okay, there can be a couple of problems here. One, say you go to a ternary system, A, B, C. Okay, and so let's say we're looking at the binary systems. So now in the binary system BC, we see that the minimum here is at B2C, and that gives energy, whatever. So find ZC equals 2ZB. And then over here, we see that the minimum is at 50% at AC. So we say, okay, ZC equals ZA. But then necessarily, if ZC must be equal to Z, you put the minimum, so I mean, I'm looking here at the AC system that gives energy as a minimum of 50%. In the BC system, the minimum's at 33%. Okay, so we fix that from that minimum, fix that because that's where the maximum ordering composition is in the AC binary. But if we put this in here, then putting these two together, obviously we're now stuck with ZA must be equal to 2ZB. Okay, and that means then that the minimum in the AB system is going to have to be over here at A2B. And that's fine if it really is. But if you go into the AB system and you find it isn't at A2B, now you're stuck, because you can't fix 3 ratios, you only can fix 2 ratios. Okay. Okay, so you can run into this problem fairly quickly when you're doing the thing. So just having a Z for each component definitely limits what you can do when you're trying to devise a large database. Now we also found that you would also like Z, as I said, you can consider within certain limits. I say Z is a parameter of the model. I mean, you can't go and put Z equal to 0.001, you can't go and put Z equal to 1,000 or something, but I mean in a reasonable range, Z from 2 up to 12 or something, you can play with Z and sort of consider that to be a parameter of your model. And we have found that with Z, as I said, when you have a highly ordered system, calciacylic or whatever, and when the Z's really are, if you have a system which is highly ordered, so the entropy really is very, very negative, very much perfectly ordered, then you really are better to have Z is small. If you have a system that's very highly ordered, if you put Z as large, then your entropy is going to go negative and kind of not so good. So it's better to have Z equals 2. On the other hand, if you have a system, and then the systems are pretty pointed anyway. If you have a system that is not terribly ordered, however, you're better to have Z is greater than 2. You get a nicer fit. Oh, well, you could maybe put in Bragg-Williams. Now, if we can play with Bragg-Williams, then we could always let Z be 2 and play with the Bragg-Williams. But I mean, unfortunately, we have big databases where we didn't do that. We played with the value of Z. Okay, and so we found that systems that weren't highly ordered, it was better to have a higher value of Z so you don't get such a sharp peak. Okay, but again, that's the problem. So if the AB system is highly ordered, you'd like low values for ZA and ZB. But if the BC system is not highly ordered, then you would like ZB to be larger. But you can't have ZB to have a different value in this system than in this system if you're going to put the whole thing into a ternary database. Okay, so as I said, had we started this whole Bragg-Williams thing, which I thought up about 4 years ago, and thought, shit, I wish we'd done that, but we didn't. So we have all these databases in which we use the Z as sort of a variable in order to make the thing rounded. So what can we do for these two problems? You can't have the ratio different in different phases. That's independent of the Bragg-Williams thing. That is a problem anyway. This problem here, well, we're stuck with it. So what are we going to do? So what we can do is we make the Z's composition dependent. And this is so I talk about here the problems which I just talked about, and here's the equations we use. So this is talking about an AB binary system. We're saying ZA is the coordination number of A, so that is the number of atoms around a central A. And we have two parameters here. We have ZAA and ZAB-A. And this is the coordination number of A when it's in a mixture of only A's. And this is ZA when it's in the AB, surrounded by ABs. Okay? And we have it vary inversely with the bond fractions. And why did we do that? Because even though it looks complicated, the mathematics, we could put ZA, I could say very linearly, ZA is equal to, this is the value of ZA in pure A, times, well, you really have to have it NAA over NAA plus NAB plus ZA in the AB system times NAB over NAA plus NAB. Make it linear, which kind of makes sense, and then I tried to start to do the mathematics, and it just got really complicated. And one day Sergei Degtyaryov said, well, actually, sorry, you gotta do it, you gotta weight them this way so that it comes out right. Said, but if we do it as the inverse, the mathematics just comes out to be so bloody simple, because if you take this inverse variation, you plug it back into the equations, you end up with something that's really simple. This is almost like those equations. Compare equations 21 and 22 to equations 2 and 3. Here you have, and putting the ZA, dividing through by ZA. Here you would have NA is 2NA over ZA plus NAB over ZB. You just have ZA in the denominator on the right side. Here you'd have ZB in the denominator on the right side. Now, when you use these equations, it's almost the same, except this is this ZA in pure A, and this is the ZAB in pure B. So very, very nice, simple equations, and the rest of it just all falls into place. The mathematics becomes deadly simple. And that's why we did it. There's no other real theoretical reason. On the other hand, this is no worse than making it linear or anything else. It permits you to vary it. So what we now have is each pure material, A, B, and C, in your ternary system. So let's take your ternary system. The linear system, the linear equation, just, I was about to give up on the thing. I don't know how Sergei figured this one out, but it worked out beautifully. Anyway, here's your ABC system. Now, pure A, you have a ZAA. And that's the same in every system in which A is part. That is the value of ZA in pure. That is ZA in pure A. Okay, then you have a Z of B, which is Z of B in pure B. And here you have a Z of C in pure C. But now in this system here, if you want the minimum, you would have a Z. This is your where your complex is. Let's say this is your complex B2C. That's where you know where your minimum is. So here you would have a ZBB. ZA. No, what is it? This is ZB. This would be ZB, BC, and you would have a ZC, BC. So this over here, this is the coordination number of C in pure C. This is the coordination number of B in pure B. This numerator here is the coordination number of B at that point. This is the coordination number of C when you have nothing but BC bonds. It's not at that point, but it's when it's completely surrounded by BCs. Okay, when there's nothing but AB bonds, that would be the coordination number of A at this composition here. And then this ratio, ZBBC over ZCBC, would have to be equal to, in this case, 1/2. Okay, so the composition of minimum ordering here, of maximum ordering, is determined by the ratio of ZBBC over ZCBC, which could be equal to this. I mean, ZBBC could be equal to ZBB. You could put this equal to this if you want. You put this equal to this if you wish, but you're not obliged to. Similarly, it's only the ratio that fixes the minimum. So what you could have is the ZB. This ZB could be 6, and this ZC over here could be 6, but each of these in the middle could be equal to 2. Or, you know, if you wanted them to be, if you wanted the coordination number to be smaller in the middle than at the ends, you could do it. So you have big flexibility. Okay, the absolute values can have certain values. The ratios, the ratio here. So the average Z could stay constant across here, or it could go down, or it could go up. And the ratio of these two is what determines where the maximum ordering is. So now you've got a lot of flexibility. I mean, if you want to make life, if you want to have the old quasi-chemical with all the Z's equal, you just make every ZA. You make ZAA, ZBB, all the Z's the same. So then over here in the AC system now, you would have ZA in the AC system over ZC in the AC system equals 1 if you wanted this to be an AC. And this could be anywhere you want, A3C, so you could make Z of A in AB over Z of B in the AB be equal to 1/4, for example. So you can set the minima anywhere you want in all three systems. You're not stuck now. at the minima points anywhere you want in all three systems. You can have the z's varying with composition across, and you have more flexibility. If you don't want the flexibility, if you wanted all the z's to be equal, make all the z's equal to 2, and you're back to the first quasi-chemical model. If you really want to have just ZA constant, ZB constant, and ZC constant, well then just make all the ZAAA, ZABA all equal to the same number, and you're back to the... If you want ZA to be constant, just let ZAA equal to ZABA, and then the ZA is constant. So you have this flexibility. And the only reason we do the inverse, as I say, is because it simplifies the mathematics tremendously. You can verify yourself if you want. It's just a linear substitution. You end up with a beautifully simple equation, and then everything else is almost the same as it was before. Okay, so that's how it works for binary, quasi-chemical, and fact stage. I think that's pretty well all the mathematics that you... All these were necessary to put in. I mean, we're trying to do this... A model, as I said, mathematically should be taken only as far as necessary. If you start to go too far with putting on too many little Baroque features, you end up with a model that becomes intractable, but you have to put in what is necessary, and we find that these are really necessary. You can't really get proper fits in the systems unless you have these variable z's. This is how we ended up doing it. We find we get a lot better fits if we use the guts type expansion rather than the polynomial expansion in most cases, although if your system only deviates a little bit from ideality, you might as well use a polynomial. That tends to be a little bit easier to look at, but this is generally a bit easier once you get used to it. So these are everything we've added here we felt was a necessary feature in order to be able to get quantitative fits to when we're doing the optimizations. But we haven't gone any further than we thought was necessary. Okay, so it's been a lot to digest, but that's the binary quasi-chemical model. Now, the ternary quasi-chemical model is really not all that terribly complicated, so that's what I'm going to try to end with today, surprisingly. Let's go to the ternary quasi-chemical, or multi-component quasi-chemical model. To show that you understand, I would think that what I said, this business of trying to prove that when omega is minus infinity, ZB over ZA is 2, you want 1.3774, that's worthwhile trying to do at home, just to play with your equations there. Sometimes you think you understand it, but you get a little better understanding when you try to do it yourself, or you find out you didn't understand. I won't go into that. Alright, number 18 is the modified quasi-chemical model, part 2. And this is where we introduce the multi-component solutions. We'll use kind of a general mathematical notation that looks kind of complicated. You'll find that all the equations here are basically just what they were in the binary paper, except now we have more than one. So here we had ZANA was equal to 2NAA plus NBB. Now it's ZANA equals 2NA plus NB plus NAC plus NBC plus NCC. It's just adding more terms. All these equations here, the bond fractions and everything are exactly like they are in the binary. We've just added more terms to them. The entropy is the same. It's minus R. This was NA log XA plus NB log XB. Now it's NA log XA plus NB plus NC plus ND. And here you have terms for every term, YAA, YBB, YA squared, YG squared, YC squared, plus you have the AB, AC, AC. You have every pair. That is pairs. It's before. And it's just the quasi-chemical model. It's the same thing that we use in the polynomial model. In the polynomial, this is it. There's really, if you look at the equations, it's all but pairs. We're not going into any triplets or anything. We're just arranging the pairs. You simply in 3 dimensions. In 2 dimensions, you had, 2 components. You had AA pairs, BB pairs, and AB pairs. Now, if you add C, you've also got CC pairs. You have AC pairs, and you have BC pairs. So you got 6 kinds of pairs to distribute over the pair sites. So the equations are just all the same. The Gibbs energy. Remember in the quasi-chemical model, not polynomial model, we said GXS was alpha AB XAXB plus alpha BC XB XC plus alpha CA XC XA, where this was the energy of the AB bonds, this is the energy of the BC bonds, these are the binary terms, times the this is the energy of forming AB bonds, times the probability of finding an AB bond in the ternary system random mixing. Here it's exactly the same thing. We would say that the delta G AB yeah, this is the term over here. So we're going to have the number of AB bonds times the delta GAB over 2 plus the number of BC bonds times delta GBC over 2 plus the number of CA bonds times delta GCA over 2. Okay, so the Gibbs energy then is going to be the energy of the AB bonds times the number of AB bonds plus the energy of the BC bonds times the number of BC bonds, delta GCA times the number of CA bonds. Or if you want to put this per mole of bonds, then this would be the mole fraction of AB bonds plus the mole fraction of BC bonds. Okay, so you're saying the total delta G of mixing, the delta G parameter is going to be the number of AB bonds times the energy of forming the AB bonds plus the number of BC bonds times the energy of forming them plus the number of CA bonds. And in the limit of a random mixture, the number of AB bonds is XAXB. So in the limit, XAB is XAXB, XBC is XBXC, and in the limit this equation reduces exactly to that equation. Okay, but now you weight delta GAB not by XAXB, but by the actual number of AB bonds, which can vary as the... Everybody happy with that? Anybody not happy with it? Okay, so you just have this, really, this reduces to the regular solution or the polynomial thing in the limit. This is just NA G naught A, this is the configurational entropy, which is just a whole bunch more terms. And this is the number of AB bonds times the energy of forming them plus the number of BB bonds, so on, and in the limit this reduces to the regular solution. So everything's all the same. This was the final thing, this was where we changed in this case we made a very slight change in the notation from what we used in kind of quasi-chemical model 1. And so this now really is the latest notation, is that the delta G, the binary parameters, I had this omega minus eta. Now what we have, we call it Q, Qij. If you're doing it as a polynomial expansion, then the quasi-chemical parameter in the Mn system is your constant term, which is the basic energy of forming the pairs, plus your terms. Rather than calling this omega minus eta, I call it Qij Mn. Okay, so those are your polynomial terms of Q's. Or you can expand it, rather than a polynomial, you can expand it as a Reddish-Gister. Okay, and I use the same notation here. We don't use that too much, but we'll do that. Or if you expand, or you can expand it as a power series in the pair fractions mm and n, and that is the same notation as last time, Gij. So a q, little q, is a polynomial parameter, a little g is the Guts parameter. And this is xmm to the I, xnn to the j. So these are either, all the Gij's are either 0, 1, or 1, 0. Well, they don't have to be. They could be both non-zero, but we rarely use those. Okay, so this notation was before this. The only thing that's new is the q's here. So this is your final notation. Okay, now, also then, there's your Kohler tube Muggiano thing, which is again is exactly the same concept as is used in the polynomial. Okay, in the polynomial we have GXS is alpha 1, 2. I'll write that out. AB, XAXB plus alpha BC, XB, XC plus alpha CA, XC, XA. That was your polynomial model. Where, remember now, when the ABC system, the question is where do you pick, if these values of alpha depend on composition of the binary systems. Where do we pick the values of the alpha in the binary systems in order to do the ternary evaluation? So we can do it like Kohler, or we can do it like Tup, or whatever. It's exactly the same thing here. These are the terms now that we're using. We're taking delta GAB. We're trying to calculate in the ternary system at that point. So we need delta GAB in the binary system AB at some point, delta GBC in this binary system at some point. If the delta GAB, of course, is constant, then it doesn't matter what point, otherwise it does, and we use exactly the same thing. We can use a Tup type of Kohler type approximation, in which if we want to evaluate the thermodynamic properties at point P, we base it upon the values of the binary parameters at these 3 points, or we could do a Tup and base it on the binary parameters at these 3 points, or we could do a Muggiano. Again, it's the same thing. The only difference is everything's the same. It's just instead of writing XAXB, we write XAB, which is equal to XAXB in a random mixture, but otherwise it's not. Otherwise, everything is exactly the same. You can use Kohler Tup. The same reasoning applies. If 1 is chemically different from 2 and 3, then you should be using a Tup model. And this should be silica, and this would be calcium, magnesium, for example. And of course, the quasi-chemical model, even in the multi-component approximation, as all the delta G's become small, it exactly approaches the polynomial model. Okay, so if all the delta G's are small and you use Kohler, you're going to get almost exactly the same thing as if you used a polynomial model with Kohler with the same coefficients. So the concept of Kohler Tup Muggiano is the same. And similarly, the Z IIs, it shows you how you would put that into the ternary system, but read it through, it's virtually the same thing as we said before. The 1 over Z1 would now be a Z11, a Z12, a Z13, a Z14, and Ij is just, you add more terms to previous equations. The interpolation formula, that's what I just talked about. This is your Kohler, here's your Kohler method. Exactly as before. In the Kohler method, you replace y1 and y2 by y1 over y1 plus 2, y2, and so on. And then we even have the same thing as before, which I just talked about it briefly in the other system, how you can pick groups, you can have weird things, you can so on, and you can choose these as well. It's exactly the same as the other thing. When you're using backstage, you'll see no difference in how you interpolate from binaries to ternaries. Are you going to use Kohler, Tup, Muggiano, how you're going to group your components together? It's the same thing. Okay. Now then, of course, so this is this whole Psi1, Psi2, so I don't want you to read all this sort of stuff here, but it's exactly, it's just taking the mathematics a little bit further, but it's exactly the same thing as in the polynomial models. Okay, and then the only difference is, then as I say, is instead of XAXB, it's XAXB, and then the software then finds the values of the number of moles of AB, the number of moles of BC, the number of moles of CA, and so on, that minimizes the entire global Gibbs energy. Okay, and then that's what so at every point, you give a point at on the phase diagram, composition point on the system, on the solution, in the ternary solution, the software writes down the equations and then finds the number of values, NAB, NBC, the number of CAs and so on, which minimize the Gibbs energy, and then puts that back in and solves the whole system. That's an additional step then of the Gibbs energy minimization. With the with the polynomial model, it doesn't have to do the Gibbs energy minimization. It knows this is NA, this is XAXB. Okay, so here it has to take the equation, it has to do an internal minimization to find the actual values of the pairs that minimize the total Gibbs energy. Then it can substitute back into the equations to give you the actual Gibbs energy of the solution. I don't think you have to read all of this stuff here unless you really love mathematics, because it's the same as in the previous paper, which I showed it on the Kohler too, but you don't have to exactly read either. And even the ternary terms are the say ternary terms. Even the interpolation. Does anybody see ternary terms? Okay. How did I know? All right.
It says on the
there are
word
yeah.
estimation of the two.
Yeah, the ternary terms have the same form as well. You read it. It's an awful lot of math because we had to put the whole thing, but it's basically, you remember in the quasi-chemical model, or the polynomial model, if you had 1, 2, 3, and you were using a Kohler based on the alpha 2, 3, then you would have a term along this line. You would have x2, the binary term would be x2, x3. You would then replace that by x2 over x2 plus x3, y2 over y2 plus y3, the ij, and then put on here an x1 to the k or something. That would be your alpha 1, 2, or sorry, 2, 3, 1 term or something like that. You take it along that line and multiply it by x1. Now it's the same thing. Instead of this not being alpha, this is just your delta G23 term. It's multiplied by a, and we use the same notation as before. Okay, before you'd have a Q term, Q, 2, 3, 1, 1, 1 would be a term with 1, 1, 1, and now it's exactly the same notation. Or if it's a guts term, it's G, 2, 3, 1, 1, 1, whatever, it's the same idea. So if you read the polynomial one, then ternary terms have the same. Ternary terms have the same meaning here. Mathematics starts to look complicated, but when you're using it the same way as in the previous. Except you're not affecting the Gibbs energy. You're affecting the Gibbs energy of the. It's not the alpha term. It's the delta G23 term. Again, this reduces. If you put in here, if your delta G's are small, and the entropy approaches an ideal solution, then these equations reduce exactly in every way to the polynomial expressions. I don't think I can really go through all these equations in the course, but read the earlier paper on the polynomials first, get that straight, and then I think this is just it's exactly the same notation. The only real difference in the quasi-chemical model is that you are rather than assuming that the bond fractions are XA, XB, there you calculate the bond fractions first by minimizing the Gibbs energy, and then okay, so you're going to have to read it through and think about it. Okay, here's the last, so we've just about done the entire quasi-chemical model. You'll be happy to know. Combining models in one multi-component solution database. So this is a big feature of what we can do in FactSage, is that we can combine the models. I talked about this before, but you don't have to have, you know, if we're deciding to use a ternary system, if we have a quasi-chemical model for this system, but these two systems were fitted previously using a Bragg-Williams model, we can simply combine them in the one database. We don't have to refit anything. And the way you do this is that you have, if you
People say this is sort of a mystery, but it's not a mystery. It's quite simple. This is a little confusing because it's written in terms of mole numbers rather than mole fractions.
But supposing I were to write this terms, this in mole fractions, if I wrote this per mole fraction, this would be the mole fraction of Mn bonds. Okay, let's just divide this through by the total number of bonds, and you would get the last term would be the number, would be the mole fraction of AB bonds times delta G AB over 2, where that's your binary parameter, plus the number of moles of BC bonds times delta G BC over 2 plus etc. That's your final term over here. So this is your linear mixing term, this is your configurational entropy term, which is always the same, and then you're saying it's the energy of the Gibbs energy of the system then is the number of a fraction of AB bonds times the binary parameter AB plus the fraction of BC bonds times the parameter BC, etc. That's your quasi-chemical model. Then you minimize, you take dg dn ij equals 0 for all the ij bonds, and you minimize the Gibbs energy. Supposing, however, that the BC system, that say the AB system and the others were fitted with the quasi-chemical model, but your BC system was fitted somewhere using a Bragg-Williams model. Okay. So this was fitted with a Bragg-Williams model in which XBC is just equal to XBXC. Okay, so all we do, you say fine, you tell the computer this was fitted with the Bragg-Williams model, XBXC, and the computer then just replaces this by, that's actually 2XBXC, 2XBXC. That's it. Okay, so when you say that the BC system was Bragg-Williams, then in the computer program, XBC is replaced by XBXC everywhere in the multi-component system. So in other words, this does not have any, this is not minimized. That's it. Okay, so you can mix your Bragg-Williams and your quasi-chemical model. Also, as I showed here, you have we say delta G can be written as a polynomial expansion, or as a Redlich-Gister, or as a Guts expansion, but it can be written as a mixture. You can have delta G as delta G naught plus a couple of these terms plus a couple of these terms if you wish. You can mix terms up. Okay, you can mix the Kohler to Muggiano any way you want. You really have complete flexibility here as to how you do things. It is now possible to mix models in one multi-component solution. This is of much practical value. For example, in developing the database for molten salt solutions, we've already performed optimizations on well over 100 common ion systems using the Bragg-Williams model, which is satisfactory. We're now including salts which the Bragg-Williams model can't be used. They're highly ordered. So ideally, of course, all previously optimized systems should be re-optimized with the quasi-chemical model, but the amount of work involved is considerable, so in the meantime, we can still put the whole thing together in one database. We're not obliged to refit everything simply because we're going to use the quasi-chemical model. Okay, and here, well, this is what I just said. If a binary system has been optimized with this, another binary system has been optimized with the quasi-chemical model, but if yet another binary system has been optimized using the Bragg-Williams model, then where the Zi is replaced everywhere simply by Yk, Yi. So you can combine all your models in systems. For those of you who really like mathematics, I'll go back to this system with no requirement to read this. Okay, this was the binary one. We got, please, okay, this has been a lot of mathematics, so I really think you should read this over carefully up to at least here, up to here. Then this is an example. If you want to read the example, you can read the example. And this business back here is only for those who like math. This is only to do with this last section 4 is an associate formalism, only has to do with computer programming. It's nothing really to do with the model. As I said, even in a binary system, and certainly in a ternary system, the quasi-chemical model requires one step beyond, if you don't know what I'm talking about, one step beyond what the polynomial model is. In the polynomial model, you simply have one expression, you have an explicit expression for the Gibbs energy. The Gibbs energy at a composition is given by this equation, and all you have to do is plug in the mole fractions and you get the delta G. In the quasi-chemical model, you got a first step. You have the Gibbs energy in the Ternary and a multi-component system, or even a binary system, is given in terms of these parameters and these bond fractions, XAB, XBC. Then you have to do a Gibbs energy minimization, an internal Gibbs energy minimization in that one phase, okay, in order to find what bond fractions minimize the Gibbs energy. Then you make your substitution. Computer-wise, when you're trying to converge, when you're trying to calculate a phase diagram or something with FactSage, you have to calculate hundreds of times. You guess as you're coming. Well, this minimization is an iterative procedure. You guess, you change. Okay. So this adds tremendously to the computer time. And we're finding that it takes a long, long time to calculate complicated phase diagrams. And then we came up with a way of tricking the computer, in which we talked about the pairs as being actual weird associates, and then we could end up making an explicit expression. I won't go through it, but if you want to read it, this was all about hugely decreasing the computer time to solve the thing by using a mathematical trick. For those of you who like mathematical tricks, read section 4, you might find it interesting. It made a huge difference in it, but this is only to speed up the system. We consider the quasi-chemical model can be written as an associate model if you make associates which contain fractions of atoms. And I mean, it's a total trick, but you can write the quasi-chemical model exactly as an associate formalism if you talk about associates consisting of A 1/3, B 2/3, and things like that. And you write the mathematics, then you can solve the thing with an explicit equation. It's amazing how it works. It's cute mathematically, but it's just mathematics to make the computer quick. Nothing to do with the actual model, nor do you have to know that to be able to use the quasi-chemical model. I wouldn't say you have to read the entire Ternary quasi-chemical paper, the number 18 here, mod 2, and understand everything, but understand the general principle. But just, if you're reading this, just remember that this is really exactly the same as this. I mean, it's really the same thing as this. It's just that instead of x1, x2, you have print x1, 2, rather than x of 1, 2 bonds rather than x1, x2, but everything else, Kohler, 2, Mugiano, Ternary terms, patern, whatever, it's all the same. We're all the same thing. Plus, we could have another polynomial in terms of the bond fractions. So that's everything about the quasi-chemical model with the one sublattice quasi-chemical model. Okay. Yeah.
You said that it is preferred to use z equal to 2 and then Bragglian instead of z more than 2 for highly ordered systems like oxide, because
for highly ordered systems, your entropy is coming close down to 0. If you use z very large, you'll end up with kind of a physically not too reasonable entropy. So you're better, I think, in that case, if you're using z equals 2, then to use, or z a lower value of z rather than a higher value of z, so the entropy doesn't go too negative. But if you're dealing with systems that aren't too highly ordered, then a higher value of z gives you a nice rounder thing. But maybe a better way of doing it anyway is always to use z low around 2 and then to put in Bragg-Williams terms everywhere, and then things would be a lot neater. But I mean, we have so many systems now that are optimized with these variable z's, and z's not equal to 2. And if the z equals 2, the other, these are, the things you'll learn later on after you've done things. Like I showed this, if you take the system silica, CaO, FeO, this system is quite highly ordered here around Ca2, SiO4. And this system is slightly ordered around Fe2, but not too much. So the result is you get, along this line, you get strong positive deviations. Okay, you get positive, the liquidus line comes down like this, goes to 1. If you try to fit this system up using the Bragg-Williams, you actually generate a miscibility gap along here, which you don't actually observe. In the actual quasi-binary system, Ca2SiO4 FeO, along this line, if you plot temperature composition, it's very, very flat, like that's what these widely spaced things mean. So you get a very flat, but you don't actually get demixing. If you try to fit this thing up with Bragg-Williams, then, as I showed the last week, you overestimate this and you actually get a miscibility gap. If you do it with the quasi-chemical model, you get what you want here. But if you use it with the quasi, but let's suppose there was another system in which this was just a little bit more, a little bit bigger. In that case, there really would be a miscibility gap. The Bragg-Williams model, though, would give you too big a miscibility gap, but the quasi-chemical model with Z is 2 doesn't give you a miscibility gap. And when I said Z is 2, okay, in this system we're using the ZA is the 1.3774, the ZB is 2 times ZA, same problem. That is equivalent to it. This is what we used in this system. And in this system, if we made this more and more negative, we still would never be able to get a miscibility gap. This would become a very, very flat, but you can't get your miscibility gap. Okay, with the Z is 2. Now, if you put in a Bragg-Williams term, or if you let Z be greater than 2, then you can get it. We also find really what we were doing too, well, even in this system we have a problem. This was fitted a long time ago. And we got a flat liquidus. Later data showed that we really should have the liquidus to be even a bit flatter. But we're stuck. If you make this bigger and bigger, because we're already at almost the limit here, additional terms would have very little effect. It's almost completely flat. We can't bring it up very much anymore by putting bigger terms in. Even ternary terms, you can't, whatever you do, you can't make the thing positive. Well, yeah, Bragg-Williams ternary terms might do it, but I mean, this is the limitation that I showed in the, with Z is 2, you cannot, with quasi-chemical, get a miscibility gap. That also applies along that sort of thing. So now we're going back and refitting this using, trying to use, but now we have to, refitting a whole big system like that's also a lot of work. We run into this trouble with optimization too. This is the subsystem then for quaternary and bigger systems. Like it's what, optimization in general, if you change the property of a pure material, then you got to change every single thing you ever did. If you change a binary, you got to at least change every ternary you ever did. And okay, but we probably, this goes way back. I wish we had used Z is 2, but put in some Bragg-Williams terms. Would have been the best way of doing it. Or at least maybe use Z a bit greater than 2, but this is a problem you run into. But you do get a much better fit than you do with the Bragg-Williams model. With Bragg-Williams, it'd be almost impossible to try to fit this thing. We did get a good fit, but luckily we don't have a miscibility gap. If there were one, we wouldn't be able to fit it, but we'd have to throw in Bragg-Williams. Does that, kind of forgot what your question was, but I think that...
Yeah, I was asking, I was thinking that you said it's preferred to use Z equal to 2 and add some Bragg-Williams instead of using Z higher than 2.
Yeah. But using Z higher than 2 would be better than using Z as 2 or not using any Bragg-Williams, I think, in such a case like this. When you have really big deviations along here, you've got to have some way of bringing that up. So.
Modified quasi-chemical model and complete complexes is the same thing as you said you like.
Well, this is the modified quasi-chemical model.
Yeah, and we put like some complexes in the model.
By putting a complex, you mean like AB or A2B?
Yes, associate.
Well, then you're mixing an associate model with the quasi-chemical model.
So
You can mix an associate model with the quasi-chemical model. I mean, you can have a complex AB, and then the complex mixes with the A's and B's quasi-chemically.
does it have any justification, physical like justification?
If in fact that's the way the system is. If the system really has complexes in it. In that case, you're treating the system, you've got an AB system, and you have AB, and you're treating them as complexes, as molecules, which go on the same lattice as A and B. So you can do that in the standard straight associate model. You simply have A's, B's, and AB's mixing randomly on one sublattice, which is the model I showed before. Or you could have A's, B's, and A's, B's mixing quasi-chemically on one sublattice. And then what this really is this then is a hypothetical ternary system, A, B, A, B, in which each of these subsystems is quasi-chemical. So the A's and B's tend to cluster, or okay, you can mix the two models. Now, by minimizing the total Gibbs energy, you're actually following a path through this system. This is your Gibbs energy minimum. You know, the whole system is not realizable. You have a path through the system, which is the path of minimum Gibbs energy. So it really is a binary system. It's not a ternary system. And this is the path that the system follows through this space, which is the Gibbs energy minimization thing. Now you have several internal Gibbs energy minimizations. You have to minimize the number of pairs, the number of complexes, and then you also have, here you have AB pairs, and here you have AB B pairs, and over here you have AB A pairs. So this is a quasi-chemical between A and AB, with a preference for A to have ABs as nearest neighbors. This is a quasi-chemical system between A, B, and B, with B's preferring AB nearest neighbors and a certain coordination number. These are the uncomplexed A's and B's perform themselves as nearest neighbors, so you have the three quasi-chemical parameters saying how the three species want to form bonds with each other, and then you have the overall minimization to give. So you can do that. Yeah, you can just enter the thing that way. What you do is you enter it as a quasi-chemical system, A, B, A, B. And if you want to enter into fact stage the associate model, you treat it as a, if you have an associate model, A, B, A, B, simply enter that into fact stage as a hypothetical ternary system, A, B, and A, B. And fact stage will figure it out. You've entered it as a ternary system, but it sees that you've only got two elements. So it'll calculate it'll minimize the Gibbs energy to give you the number of ABs that minimize the Gibbs energy. Here you enter the same thing, a G naught A, a G naught B, a G naught AB, and then you can also enter your... Now when does that work? It works really if you really believe that you have complexes. Or sometimes, well, when we get into more complex, into real solutions, I'll be talking an awful lot now about systems A, B, C. I'm going to pretty soon be talking about real solutions of slags and salts and metals. Then we can see where sometimes the associate model does have some advantages.
Complex is like compound. A compound can be complex. Very stable compound is different.
I wouldn't say not in a metal system if you're dealing. I don't believe any of these metal systems. Not really, no. You're not getting at molecules that are occupying a single sublattice. But, okay, it's got complicated where you want to, I'll show you some examples later where we actually do use the associate model. Not because you really have associates, but because it's the only really proper way, the only way we can think of doing it at the moment. We're using something we don't really want to use, but it's the only way to really get around the thing. But no, in general, I don't really believe that very many solutions really have molecules in them. Especially big ones. I mean, if you have something like, CA3SiO4, I mean, there's no big molecule like that. It's not possible. Sometimes you almost, because there's really no other way to fit something, we're kind of forced to do it. But, or the other reason is that, well, it's too late. I'll do this on Tuesday. What do you do if you have a system with several propositions of ordering? I'll talk about that on Tuesday. Okay, I have a couple of problems you can play with. There should be on the map, these 2008 to question 4 and 2009 to little questions to do for next week. But since this has been the heaviest mathematics, I would recommend that next week you read over what we talked about so far, especially the number 17, the binary quasi-chemical, and then the ternary quasi-chemical to get the general idea. But remembering that all it really is the same as the Kohler-Tube-Luciano, but with minimization. And then next week we go on to sublattices and long-range ordering. Followed then by a bunch of stuff about how this all applies to oxides, slags, ceramic systems, salts, metals, various classes of solutions, sulfides. What models apply best to different systems and so on. That's what I plan for the rest of the course. Don't know whether we should have 2 more tests or just a final exam. Have one more exam and then a final, or just the final? I think it's better for you if you have 2 more. Yeah, gives you a chance to spread things out a little bit. So you might have one in a couple of weeks on some of the theory and then one at the end on the whole thing. Or often the way it works out is we have the second quiz only a couple of weeks before the end. And then the final quiz gives you a chance to redeem yourselves if the... Okay, I already talked about November 8th and 17th, I won't be here, and they're replacing my other...
So when we turn this off, turn it off, Jenny? Jenny? You turn it off, okay.